Okay, so we're starting 9.3, which is estimating population standard deviation. Okay? So what I'd like to do, up to now, we've been using nice symmetric distributions. Today we're going to break that rule. Today I would like to introduce to you the chi-square distribution. Now, it looks like an X, but it's the Greek letter chi, and it's squared. Okay? So a lot of times we will write that out as the chi-square. Don't call it chi. It's not Chinese. It's Greek chi. Okay? All right. So the chi-square distribution, the equation, you don't really need this too much, but I'm going to give it to you anyway. N minus 1 s squared over sigma squared. That is your chi-square distribution. Once again, just like the t distribution, it has degrees of freedom. Your degrees of freedom equals n minus 1. That will change in a future chapter, but for this chapter, we're still sticking with the n minus 1. So don't get married too closely to that idea. Now, some properties of the chi-square distribution. Number one, it is not symmetric, which is, I mean, it'll be okay. It's not going to be too bad, but we're going to miss symmetry, okay? Number two, it is always positive because we're squaring our distribution, okay? So, or 0. Maybe I'll put an or 0 there. It could be a 0, but it's never negative, okay? Number three, the shape changes based on your degrees of freedom. And when I say it changes, it changes. So let me pull up an example here. Okay, let me share the screen here. Oh, you can't see the board. I was working on a calendar for my other class. All right, where is it? This is what I want. Okay. Now, I'm not quite sure why whoever did this graph, it's a really good graph, but for some reason, instead of putting degrees of freedom, it's okay. It represents degrees of freedom. So if your degrees of freedom equals 1, it's the yellow line. Does that look symmetric to you? Not even close. Number 2, degrees of freedom 2 is the green line. Not even close to symmetric. Degrees of freedom 3 is the turquoise line that starts here at 0, goes up. Goes like that. I mean, this changes pretty dramatically, right? Degrees of freedom 4 is the blue line, 6 is the purple line, 9 is the red line. Okay? So especially when you have small degrees of freedom, this shape really changes a lot. Okay? Not even close to symmetric. Okay? So just kind of keep that in mind. Because of that, let's talk a little bit about some requirements here. Requirements. Number 1, it must be a simple random sample. And 2, the population must be normally distributed. Okay? And this is going to be very strict. Because basically, how you get the chi-square distribution is you take a normal distribution and you square it. And when you do it, it ends up looking like a lot like all these other crazy things. Okay? So let's talk about the confidence interval for population standard deviation. Okay. Now in the past we've done plus or minus. We can't do that with this one because it's not symmetric. Okay. We're not adding and subtracting the same values. Okay. So what I'm going to do is I'm going to write it this way. Your sigma is going to be between n minus 1 times s squared over chi squared on the right, and the square root of n minus 1 s squared divided by chi squared on the left. And notice the left is on the right and the right is on the left. Okay. We'll talk about that. That can be a little confusing. Here's what I'm going to say. Just remember, when you're writing your confidence interval, it's always the lowest number before the highest number. So the idea here is, let's go ahead and look at our table here.
Only one has a square root.
Oh, sorry, they're both supposed to be square rooted. Yes, thank you. Good question. Yeah, both should be square rooted. All right, so let's pull up our table here. Chi-squared table. Now, once again, I'm going to emphasize that you look at the picture. Okay? Now, because this isn't symmetric, you got to think about this differently. So they kind of drew a generic picture. They purposely made it skewed. Okay? So if your alpha, in this case, they've got alpha here, it's giving you the area to the right. Okay? Now here, if you want your alpha to be here, notice they did not split that in half. This is the whole alpha. Okay? If you want your alpha to be on the left, then what you're doing is you're going to say, I want 1 minus alpha. Okay, they're not splitting this in half. They can't split it in, the reason why they can't split it in half because it's not symmetric. Okay? Now, if you want to split it in half, notice these two do not look symmetric because they're not. It's not symmetric. So if you want to do a confidence interval, and if you want half of your alpha here and half of your alpha here, well, the chi-squared on the alpha on the right, the chi-squared of alpha over 2 is normal. It's what you would find here. And then you're going to do 1 minus half of your alpha. Okay, here's what I mean by that. So let's say that I want to find a 95% confidence interval for degrees of freedom equal, what do you want it to be? 14. Okay? So here's what we're doing. We've got 14 degrees of freedom. Okay? Now, it also tells you here, it's giving you the area on the right. Okay, so once again, a picture can be helpful. Okay? This time it's not symmetric, so I'm going to try it out. Now, most of them don't start at the top, unless you're at 1 or 2. So this is kind of your generic picture. Now, if I want a 95% confidence interval, how much do I want in each tail? I want 2.5% here, and I want 2.5% here. Okay? Now, the nice thing about this is, okay, so let's talk about the 2.5% on the right. Okay? So I'm going to look at 0.025. Which is this sign, and I've got 14 degrees of freedom. Okay, so this value here is 26.119. Okay, so this value here is 26.119. That's the chi-squared on the right. Now remember, the right's going to go on the left when you do this in a minute. You're going to see why in a minute. Okay, now, this gives me the area to the right. I want 2.5% to the left. So how much area is to the right of this value? 97.5%. Okay, that's what I'm going to look up. So I'm looking up 97.5%, 14 degrees of freedom. That gives me this value of 5.629. Okay, does that make sense? So this value here is 5.629. Okay? All right, so let's do an example ahead, you've opened up Excel. All right. So let's say that I want to find a 90% confidence interval for the population standard deviation for a 3-year-old Chevy Corvette. Okay, so we've got the following data: 41,844, 36,995, 41,995, 36,995, 41,500, 40,990, 38,900, 43,995, 39,995, 39,995, 37,995, 42,995, and 35,950. Go. And by the way, what's that? Bigger? It's going to be.
It's just that I was actually write all this stuff down so we have the same stuff.
Is that helpful or not helpful? Because if I make it any bigger, it's not going to fit on the same screen. You want that? Okay. I'll make it smaller in a minute so you can actually see this. Now, by the way, just FYI, my dad died, as you know. He bought an electric car, a Nissan Leaf, 4 years ago. It was $38,000 brand new. I'm trying to sell that thing for $12,000. That's crazy depreciation, and it's 4 years old. So it's a fun car, but I would never pay that kind of money for a car. At least the Corvette holds its value, I guess, right? What are they brand new? Anybody know? What? How much are they?
Around 70 grand.
70? Oh, that's a big depreciation too. Wow. I would. Yeah. My wife loves Hondas, but all right. So at any rate, so we want to find a 90% confidence interval. How would you do such a thing? Bueller.
Chi-squared equation.
We're going to use the chi-squared equation. Okay, so if we look at the chi-squared equation, we need to know our n, right? Our n in this case is 13. We need to know our s, right? I'll figure that out in a minute. We need to know our chi-squared on the right and our chi-squared on the left. That's all we need, okay? Now, you technically don't need the mean, but why wouldn't you get it? Don't you want to know how much these are? Okay, I'm curious anyway. The mean is what? Average. And in fact, I think that you guys, just when you get a data set, so $40,000, you should just find the mean and the standard deviation just as a habit. Everybody wants to know that on every data set. Plus you need it for your formula. So $2,500, right? Now I need to figure out my chi-squared on the left, my chi-squared on the right. So if I go back to my picture here for a second, okay? So if I've got my picture, now I want this to be a 90% confidence interval. Here, I'll pick a different color. Like, what's in the contrast? Green. 90%, okay? So that's not that number anymore. Okay. How do we find this value chi-squared on the right? I'm going to want 5% here, right? 5% of each of those. Okay. Oh, by the way, what's my degrees of freedom? 12 degrees of freedom. Okay, so I got 12 degrees of freedom. So I want 5% on the right. Let's share this. Okay, so 5% on the right, 12 degrees of freedom on this row, This is value. 21.026. So this value is 21.026. Now, what's this value here? What column am I looking at? 0.95. I'm at the 0.95 column. 12 degrees of freedom, 0.95, 5.226. I don't know if that was the same alteration, but it was similar. Okay, so I'm going back to this equation here. Now here's the deal. I know that this is right and left, and this is right and left but backwards. Okay? Here's the deal. All you got to do, so if you take the bigger number here, that's because it's in the denominator, this is going to be smaller. And if you put the smaller number here, that's going to be the bigger number. That's why they're backwards. Okay? You're dividing by the big number, so it's smaller. You're dividing by the small number, so it's bigger. That's another way to think about it. But at any rate, I get these mixed up all the time. Doesn't matter. Just when you write it, it's always low number first, then the high number. Okay? All right. So let's punch it in our equation here. Okay? So my lower, my upper. Okay, let's write down our chi-squared on the right should be 21.026 and 5.226. Okay? All right, Trevin, help me out.
All right, so you do for your lower 12
Equals the square root of
12 times 5
12 times
your s, which is
s squared, right?
Yep.
S, right. So we really want the variance here.
Divided by
Divided by.
lower, so your left x.
So that's going to be the chi-squared on the right. Correct?
What would be your right? Your lower?
The chi-squared on the right is going to be my smaller number.
Is that your lower?
That's going to be my lower limit. Yeah, it's backwards. Once again, just fix it if you get confused. Okay. So 1891. And I'm going to copy, I'm going to paste this, except for I'm not dividing by the right anymore. I'm dividing by the left. The bigger number, so it's going to be, or the smaller number, so it's going to be bigger. Okay, now let's think about this for a minute. So I got 1891 to 37. Now let's just compare this. Okay, as we compare this to the lower, that's what, a $600 difference, right? But if I compare it to this one here, that's a $1,200 difference. Did I make a mistake? No, because it's not symmetric. Okay, so going back to my picture here, okay, the idea here, so this is your standard chi-square distribution. Okay, if I'm doing a 90% confidence interval, my lower number was 1891.57, so this number is 1891.57. My higher number is 3794.16. And I got a value here of 2503.86, which is kind of where the peak is, right? You would expect your standard deviation to be around the peak, wouldn't you? Okay. But it's definitely much closer to the low side than it is to the high side, because it's not symmetric. Okay. Yes.
How do you know when to use the chi-squared equation as opposed to something else? Does it have to specify in the problem this is not normally distributed?
Well, we should have made we made the assumption that it was normally distributed. We just made that. But how do you know? Because it's asking for the population standard deviation. So if it's asking for the population standard deviation, plus it's, when you think about it, it's squared. Notice in my formula here, I'm really asking for the variance. Okay. Now, by the way, if I asked you for the population variance, okay, the sigma squared here, I would not need those two square roots, right? Sometimes I can do that on the test without thinking, so I just don't square root it. Okay? It's easier, I think, to think in terms of, in fact, if you wanted to, I could find the population variance. Well, it's just going to be that raised to the second power, right? But I don't like to do that because then you're like, oh, plus that's a huge number. What does a variance of $14 million mean to you? I can't even think like that. That doesn't even make sense. So your standard deviation makes a lot more sense. But I will just say this: we're not done with our chi-square distribution just yet. We're actually going to be doing a test probably after spring break called the analysis of variance. And so we're going to bring back the actually a new distribution called the F distribution. The chi-squared twice. Which means we got two sets of degrees. Yeah. Okay. Now we're talking. Now we're getting into some good statistics here. All right. So quiz tomorrow at 9.3. We will review your old tests tomorrow, and we'll review anything you want to review here. Oh, by the way, I forgot to mention, how do you find these values if you're not looking at the chart? Equals chi-square, which one? Now look at this. We got the left tail, we got the right tail, and we got inverse or not or dis. Which one do you use? The inverse, okay, so if I'm doing the left tail, how much do I want in the left tail? 0.05 with 12 degrees of freedom. I should get an answer very close to 21.026. Oh, I did the left side, sorry. Okay, and if I'm doing the chi-square inverse on the right tail, how much do I want in the right tail? 5%. So this one's kind of nice with 12 degrees of freedom, and hopefully I get 21.026. I did. Okay. So the Excel is actually a little bit easier to use in that diagram chart. Okay. Quiz will be on the chart tomorrow, though. Okay. See you all tomorrow. Thank you. Stop recording.